All right. Thanks, Chris. Hopefully all of you are seeing my slides. Hello, everyone. As said, my name is Ramin Bostanabad. I'm an assistant professor here at UCI. And the work that I will present today was actually done almost 2 years ago when I was a student at Northwestern University working with Wei Chen. Well, I'm absolutely positive that all of you are familiar with Gaussian processes. If you're not, think of them as a natural extension of normal or Gaussian variables, except that instead of working with numbers, you'd be working with functions. Now, Gaussian processes have many benefits which underpin their widespread use in engineering design. However, they also have some disadvantages. One particular disadvantage is that of scalability. As I'm showing at the bottom of the figure, as you increase the size of the data set, the time that it takes to fit the Gaussian process increases quite a bit. Now, obviously, we're not the first who try to address this scalability issue of GPs. People have looked into it in the past, and this is just a very few works that come into mind when you think about the scalability issues of GPs. However, in our work, we wanted to address this issue in a different way. Our approach is actually very similar to the idea of bagging. What happens in bagging, if you're not familiar with it, is that given a data set, what you would generally do is that you pick a set of models instead of just one. For example, you would pick a deep neural network, a Gaussian process, a polynomial function of some degree, a random forest, a tree, and so on and so forth. And then you keep getting samples from your trained data set with replacement, and then you fit each model to that. And then when it comes to prediction, you use all the models to do prediction, and then let's just say you average the results or look at the median or something like that, and then report that. Well, what we did with Gaussian processes is a little bit similar, but it is also different in two important ways. The first one is that we're not using different models. All the models we use are naturally Gaussian processes. The second difference is that we don't actually fit different models or different Gaussian processes. We just fit one Gaussian process and come up with a mechanism that allows us to use the hyperparameters of that Gaussian process in all the rest of the Gaussian processes. And this essentially allows us to save a lot of time when it comes to developing the model and then spend that time and efforts on the application. The application being the design of metamaterials. Now, metamaterials are drawing significant attention in a wide range of fields over the past couple of years because to start with, they can achieve unprecedented properties. Traditionally, these methods are designed with topology optimization or multi-scale topology optimization. However, these sophisticated methods, they have a lot of details, and they may not be the optimum way to tackle this problem, especially in the early stages of design when you want to go through a lot of iterations and you want to see what happens to the performance of your structure, whether it's compliance or some other property, as you're changing the topology of your unit cells or the structure as a whole. Now, to address this, we wanted to take a data-driven approach. Now, this approach, similar to other data-driven approaches, has essentially four pillars. We start off by generating a large enough data set. Once we have that large enough data set of unit cells, which hopefully represents a wide range of unit cells, either in terms of the topology or in terms of the property that they have. Once we have that data set, we essentially go ahead and simulate each and every one of them to find out their respective properties under, let's just say, some loading conditions or under operation conditions. At this point, we have a training data set, and then we can fit some sort of a machine learning model to it. This is the step where we use GAGP. And one of the reasons that we actually use GAGPs is that it allowed us to kind of validate some of the assumptions and the methods that we had used in the previous stages. And I'll talk a little bit about that over the next slides. Once we fit the machine learning model, again, that's a GAGP in our case, we're going to be using that in some outer loop application, which allows us to not only amortize the time and effort that went into steps 1, 2, and 3, but it also allows us to do actually gain a lot of time down the road and also do maybe some studies and gain some insights in terms of what happens to the physics of the problem. Now, in our paper, which again was published maybe around two years ago, we go into the details of what happens and what goes into each and every one of these steps. Here, I just want to point out a couple of things. The first one is, obviously, a unit cell is a very high dimensional input, and it's not really efficient to directly use it into the meta modeling part when it comes to GAGP. So what we did is that we used the physics of the problem. In particular, what we did is that we did some spectral analysis on each of the unit cells, and by doing so, we found their so-called Laplace spectrometry, or LB spectrum. Now that we have the LB spectrum, we can use that as input into GAGP. But what we did is that we didn't use the entire LB spectrum. We wanted to do some sort of a dimension reduction or extreme dimension reduction. And here where the idea of eigenvalues and their importance comes into picture. So we know that the larger eigenvalues are more important. So we just want to use maybe the first 15, 16 eigenvalues in our analysis. Then the question is that enough? And do I have to take an iterative approach to essentially, let's just say, start with 16 and then increase it up all the way to maybe 15? This is where one of the nice properties of GPs comes into picture. Now, when it comes to fitting a GP, there are some hyperparameters known as the roughness or scale parameters, which I'm denoting by omegas here. Once you fit a GP, you can directly look at the estimates of those parameters and realize whether or not an input is important when it comes to affecting the response in your data set. Now, the response in our case is essentially a property of the unit cell. Now, if you look closely, you would see that the omegas of the roughness parameters that correspond to eigenvalues 14, 15, and 16 are very small. Note that the figure on the bottom right is in the large scale. What this essentially shows me is that I actually don't need to consider the last three eigenvalues, that is 14, 15, and 16 in my data set. I can simply use the first 13 eigenvalues to essentially and effectively learn the property of the unit cell as a function of its topology. Now that we have GAGP or any other machine learning model for that matter, we can use it for outer loop applications. One of the things that we use it for is inverse design. So essentially what happens here is that I'm interested in having a unit cell with a target property, right? So I'm going to put my GAGP in an optimization loop where I'm going to be looking for a unit cell with a target property. Now, in the paper, we actually do this for a couple of different applications and case studies, and we show that, first of all, having big data helps in terms of identifying diverse unit cells, which can have similar properties. This allows us to have that design flexibility, which is very desirable. And second, in this particular study that we did, just for example, because of the data and how we did the dimension reduction, GAGP actually outperformed neural networks a little bit. Now, since then, my colleagues at Northwestern actually have extended this work in quite a few directions that I want to point out two of them. The first one is on designing multi-scale metamaterials while ensuring that they are manufacturable, in the sense that we want to use different unit cells at different scales of the design, but at the same time, we want to make sure that they are actually manufacturable, they stitch together, right? Now, the problem or the difficulty with such a problem is that you're going to be working with mixed variable when it comes to data mining or fitting a meta model, because understanding how you would identify or classify a unit cell is not a numerical variable that you can directly use in some sort of machine learning model. It's a categorical variable. Now, if you do not have big data, this becomes an issue. If you do have big data, of course, go ahead and use some sort of a neural network. But if you do not have big data, which can be the case in complex problems, especially if you're trying to do 3D, you're going to use different versions of GPs. In particular, there are two versions of GP, LVGP and LMGP. These are highly efficient in building surrogates to data sets that have both numerical and categorical variables. The second work that I want to mention in passing is essentially an end-to-end multi-scale materials design pipeline where deep learning, and in particular variational autoencoders, are essentially used to unify the dimension reduction and the meta modeling part that I just talked about. Now, in this talk, essentially, and in the previous talks, we actually talked about many different methods that comes into data-driven design. I think data-driven design, especially when it comes to materials and metamaterials, faces many challenges, and I believe those challenges should be perceived as research opportunities. For example, how do we design multi-scale metamaterials that go beyond optimizing the compliance? How about local stresses, hot zones? This is extremely important when it comes to understanding how, for example, these materials behave in extreme conditions. What I think we need to do as a community to address these challenges is essentially to do three things. The first one is we got to develop methods, algorithms, and tools that are versatile, scalable, and transferable. Second, we got to make a lot of data and make those data publicly available. And third, last but not least, we got to make sure that we go through a multifaceted education. With that, I'm going to thank you all for your attention and open the virtual floor for questions.